get started. Good morning, everyone. Thank you for joining us for another EI Live K-12 session for students and educators, a series of the Columbia Climate School. My name is Adrienne, and I'll be facilitating the session today. For those of you who are unfamiliar with the Columbia Climate School or who are joining us for the first time, we are a newly established school at Columbia University for cross-disciplinary climate research. The school marshals the university's strengths in basic and applied sciences and expands its resources to understand the climate and its impact on society. The Climate School is the first new school at Columbia University in over 25 years and incorporates the Earth Institute, which includes the Lamont-Doherty Earth Observatory, along with more than 20 other centers and several hundred people who collaborate among many departments across the university. What we're hoping to do with these EI Live K-12 sessions is to introduce you all to our interdisciplinary work through our scientific experts. These bi-weekly sessions will run throughout the whole semester, and if you'd like any more information about them, don't hesitate to contact us. Each week will focus on a certain topic and will be directed towards a particular age range. Today, this session is Unearthing Microfossils, Keepers of the Earth's Climate Record. During today's session, we'll be learning about the Lamont-Doherty Core Repository, which is home to one of the world's largest collections of ocean floor samples called sediment cores. We're joined today by Nichole Anest, who is the curator of the Core Repository at Lamont-Doherty Earth Observatory. We will have time for questions at the end, so please use the Q&A box because the chat is disabled. The session is being recorded, and we will send participants the link for the recording after it's complete. And with that, I will stop talking and turn it over to Nichole.
Hello, everybody. My name is Nichole. I can't see myself, so I assume everything's working. Okay. Hi, I'm the curator here at the Lamont-Doherty Core Repository. And today I'll be talking to you briefly about our collection of sediment cores, which are basically tubes of mud. Ours are mostly from the bottom of the ocean. But then I'll be talking about what we see in the mud and how we use it a little bit. So on the screen here, you can see a map of our collection. You can kind of make out dots all around the world in the oceans. Each dot represents one of our samples. So we have just over 20,000 tubes of mud from the bottom of the ocean floor. And we're the only collection that is truly global. There are several repositories in the United States as well as internationally. But most of them are focused on a specific geographic area and not truly global. So how do we get mud from the bottom of the ocean? So a research vessel, a large ship, goes out into the ocean over a predetermined area. They lower a tube, an empty barrel, could be 20 feet long, could be 160 feet long. They lower this over the side of the ship. At the top of it, you can see, if you see my mouse here, this blocky part is a head that can hold a series of weights, up to 1 ton of weight. So it depends on the type of sediments we think we have to penetrate. That decides how much weight gets put on top. But the barrel is literally just lowered slowly to close to the ocean floor, and it's allowed to free fall for the last, say, 30 to 40 feet. And so the only thing pushing it into the mud is all the weight that we put on top. Now the mud everywhere, not just at the bottom of the oceans, gets laid down, right? You get a new layer, new layers build up on top over time. So the deeper we can go in the mud, the further back in time we are actually going. So here's a core that was taken in the Long Island Sound just a few years ago. And it's taken, so the barrel, the metal barrel, has a clear plastic liner inside of it, so that once the core gets pulled up onto the ship, we can just push the plastic out and we don't have to disturb the sediments too much. So through the clear plastic liner on the left here, you can already see that there's some stratigraphy, that we can see the layers in the mud. And then once we split the core open, as you can see on the right, you can see that there's this big color change that you can see through the liner, but there are also many smaller layers going on that we can look at and figure out what has happened in the Long Island Sound over time. The Long Island Sound in particular, though, has a lot of areas near the top here. You can see that it's not just smooth layers, but that it's like a little jumbled up, right? There's a lot of storms that come through our area, and all of that will show up in a sediment core. Briefly, here's a snapshot of an actual core being pulled up onto the deck of a ship. This was in 2007 off the coast of Portugal. And this is a relatively short core where the pipe, that plastic pipe that you see there, is only 10 feet long about. But you can see that it's a lot. There's a crane, right, with a long winch of a long wire hanging down. And you have all that weight. So when you're out on deck on these coring cruises, you can see how the people are dressed. You have to have a hard hat on. You have to have steel-toed shoes or boots, life vests at all times, because there's a lot of things moving around, a lot of very heavy things. And of course, right, if you get waves going on as well, it just makes everything that much more exciting. So mud. There's a lot of it down there at the ocean floors. But it's all different depending on where in the ocean you are. So we can find a lot of different things in the mud in our cores. We can find mineral grains, which are just broken down rocks. We can find volcanic ash, all different types of clays, and the shells of different types of plankton, right? So there are many types of plankton. There are trillions in the water today, and some of them build shells around themselves. When the creatures die, their shells rain to the ocean floor, and just pile up. You can have hundreds of meters of sediments in the bottom of the ocean that are nothing but plankton shells. So from this map, you can see that there's terrigenous mud, which is stuff directly from the land that's near the coasts of the continents, which is what you would expect. The yellow clays here, yellowish orange. Clay is something that's super tiny, less than 63 microns in size, and it's mostly wind blown into these areas. Excuse me. The blue areas are carbonate ooze. So carbonate, calcium carbonate, that's what makes up chalk. That makes up foraminifera. They're a type of plankton that we'll talk about in a couple of minutes. But that's what it, so an ooze means it's mud that's mostly made up of plankton shells or biologic debris. So carbonate ooze, you can see it makes up, at least half to 3/4 of the mud at the bottom of the oceans. And then you have silicious ooze, this green color. It's not actually green, but silicious ooze is the same thing. It's silica-based plankton shells instead of calcium carbonate based. And you can see that it's all around Antarctica, the west coast of South America, and then there's like a weird tongue that sticks out in the Pacific, and some in the Indian Ocean. The silica oozes are found in very nutrient-rich waters. So along the west coast of South America here, there's an upwelling. So the bottom currents or bottom waters are coming up to the surface along the west coast of South America there, and they're bringing a lot of nutrients with them. So here we have, different types of plankton. And these plankton shells are what, when they rain to the ocean floor after the creature has died, they become microfossils, right? So tiny things. We can see most of them with the naked eye because they're about the size of a grain of sand. But there are some that I don't have pictures of here today called coccoliths, which are nanofossils. So that means you can't see them with the naked eye. They're very, very tiny. As a matter of fact, these guys here, radiolaria, because they're tiny animals, and foraminifera or forams, which are also tiny animals. They'll actually eat coccoliths or work in have symbiotic relationships with them. So like I just said, radiolaria here at the bottom, they have a silica shell. They're tiny animals or zooplankton. Diatoms, top left here, they're actually algae or a type of plants. So they're a phytoplankton. All of these microfossils, or all of these species, have been around for hundreds of millions of years. And especially the forams that we'll talk about, when they're living and building their shells, they're using the chemistry of the seawater in which they're living. And that chemistry changes with the Earth's climate. So we can actually use all these tiny little shells as little recorders of Earth's climate history. Excuse me. So forams, like I said, they've been around for a very long time. As well, over 500 million years. There are over 50,000 species of them. Their shells, like I said, are calcium carbonate, and them, along with the caucasus that I just mentioned, they make up all the chalk on Earth. They're shells that get crushed through time, so that you get so many built up layers of them that they just compact and crush themselves. And then, yeah, you get things like the White Cliffs of Dover. Things like that, these huge beds of just calcium carbonate that build up. And as you can see from the pictures, I'll go back again, right? You can see how varied some of the species are, especially in the forams. You can have very long and skinny ones. Most of them are circular in some form because as they grow, they grow by building a new chamber and moving into that new chamber in their shells. And here you can see on the right a living one. And so all of these plankton are single-celled organisms in the case of forams, right? They're tiny animals. And through their shells, in the bottom left, you can kind of, bottom left picture, you can kind of see that there's pores or tiny little holes all along the shells. And in the right picture, back to the living one, you can see that they have little filaments or pseudopodia that they stick through these tiny holes. And that's how they catch food or where little tiny caucasus or other phytoplankton algae would live within them as symbiotically to help them produce energy. So as a first step, a first order, you might say, microfossils can tell us many things. They can tell us how deep the water was, how hot or cold the water was. They can also tell us beyond the temperature of the water, what Earth's climate was like over time. And just looking at a small snapshot of the water column, this image here only covers the continental shelf, right? So it's it doesn't go very, it's just a couple of 100 miles from like the beach, as you would say. It's not the deepest part of the ocean, but already you can see that at different depths within here, different species like to live, right? They so when you look at a core and you look at an assemblage of foram shells, you can immediately tell approximately what kind of water depth you're talking about. If it's tens of meters, hundreds of meters, thousands of meters, just by the types of shells you're seeing. So you don't have to do too much work yet to get much more detail. And there are people whose entire careers are based solely on studying different types of species, right? They'll study forams or diatoms or radiolaria and really become experts in what makes, you know, the best, where certain species live and how they evolved through time over hundreds of millions of years. There are many people studying living analogs, living forams, diatoms, radiolaria. Forams in particular, though, because they have a calcium carbonate shell and they are very sensitive to how acidic the ocean waters are, people today are studying living forams just to see how broken down their shells do get in current conditions so that we can better understand what we see in the microfossil record. We can also tell how hot or cold the water was, right? If it was polar, as you see here in this example, there's only one polar species, so only one species of forams in this example that likes the coldest waters. Most of them, as you can see here, are tropical to subtropical, a few leaking out into colder waters. But so we can also tell based on the assemblage of foram shells that we find, right, relatively how hot or cold the water was or how it's changed through time, just by looking at the different species shells that we find. And like I said, there are 50,000 known species of forams going back over hundreds of millions of years. So yeah, so there's a lot of different species to learn and learn how to identify, because you might be able to tell that many of them are very similar looking. So it does take quite a trained eye to be able to decide which species you're looking at sometimes. And now we get to microfossils telling us what the Earth's climate in general was like, and more specifically, how much ice was tied up on land. So what the ice ages, when the ice ages were. And we can do this specifically with forams because of oxygen isotopes. And I know this is a jam-packed presentation, but hopefully, you know, if you take note of any questions you have, I'll be able to answer them. But so isotopes are basically different, you know, an element with a different number of neutrons in its nucleus. So some are heavier if they have more neutrons, or lighter if they have less neutrons. In the case of oxygen, the two main types of oxygen are oxygen 18 and oxygen 16. So 16 is lighter than 18. So it's preferentially evaporated from seawater. So in a non-glacial period like today, which we call an interglacial, you have oxygen 16 preferentially being evaporated, rains down onto the ground, but then it's returned to the ocean basins because of as runoff from the land. During a glacial period where the Earth is overall much colder, and so you have ice, miles of ice being collected at the poles. For instance, right here in New York, where I am, right, there was a mile of ice above right here about 11,000 years ago. Well, 11,000 years ago is when the ice age ended technically here. So during a glacial period, you have that light oxygen being evaporated off, but instead of being funneled back into the oceans as runoff, it's now captured on land as ice. So the ratio of oxygen 16 and 18 changes during a glacial versus an interglacial. And so we can pull out that ratio of the different types of oxygen from the shells of forams to tell us how the ice ages have come and gone over time. So here we have that record going back just over 5 million years. We have a record from the change in oxygen isotopes, benthic meaning they were using bottom dwelling forams for this study, but going back 5 million years. So the present day is on the right, and you go back in time towards the left. And you can see that this blue line, which depicts this change in the oxygen isotope record, is very jagged, right? It goes up and down a lot. The up being warmer and down being colder. The gray line that's at 0 on the left-hand scale that crosses the thing is an average. It's equivalent to today's temperature, so we can see how the Earth's climate record has changed relative to today. You can also see, right, about 2.5 million years ago and further back in time, it was a little bit warmer than it is today. But then overall, right, it's been a cooling trend, right? The blue line is overall going down, sloping towards the present day, with a few excursions to the line. Today, our line is about 2.75 on the right-hand scale. That's where we are today. But you can see at the bottom right here, you have these 4 low peaks. With one that's closer to them. And most of these, a lot of these throughout the past few million years are also ice ages. They just weren't as cold as today, as the last ice age rather. And the bottom graph is a close-up of just those lowest 4 or 5 peaks, showing you where the ice ages occurred. and the interglacials. So our last glacial maximum, that means the height, the coldest part of the last glacial period was about 20,000 years ago. But yeah, so very briefly, right, we've been able to tell what the Earth's climate history has been going back over 5 million years, just from, well, from the shells of these tiny little plankton. The equivalent Vostok delta T on the left here, that's an ice core. So most of the climate records, the historical climate records that you see, have been tuned. So they've been statistically modified to match up with the temperature changes that we see from the ice cores, because we're able to get those at higher resolution. So in the oceans, the resolution of data is on the scale of, sometimes you can get 1,000 years in the deepest part of the ocean, but it's most likely somewhere between 1,000 and 10,000 year resolution, because sedimentation rates are so low, we can't tease out anywhere near like annual signals in ocean cores. But from the ice cores, you can get close to hundreds of years, if not just 1,000 or a few thousand year resolution. So they're a much higher resolution record that's easier to work with. So we can adjust the signals that we get from our data to match up with the temperature records. So now I'm going to show you what the first step is in finding out and getting this kind of data out of your muds. The very first step is to actually wash the mud. So you pull up this long record of Earth's history, sample it at different intervals, and a sample would be just scoop out a little bit of it, excuse me, and then you sieve it through a 63 micron sieve, and that's to remove the clays, which will get saved if people want to work on them. But it's much easier to work on things in the coarse fraction, right? Anything above 63 microns. It's easier to see larger sizes, so they have more weight. And a lot of the analysis on these shells, you need a certain amount of weight of the shells, not just a number of them. So it's overall just easier to work with the coarse fraction. So in a second, I'm going to share my other screen. I'm going to stop sharing this one. Right here. And if there are any questions, I'd be happy to answer them now while I'm setting up my other camera.
I don't think we have any questions yet in the Q&A box, but if people have any, please put them in there and we will get to them. I was actually curious, Nichole, how do you decide where to go to take samples?
So that depends on the researcher and what they're looking for. For a long time, the North Atlantic was heavily sampled and studied because you have a lot of icebergs discharging in the North Atlantic. So it was a good place to study ice ages in particular, because the flow of icebergs leaving the Arctic, would increase or decrease with the ice ages, right? You get a lot of ice building up during the ice age, and then as that ice starts to melt, icebergs are discharged and move into the North Atlantic. And again, another record that's been used in the past for icebergs in particular was shipping lanes. Captains would take note of icebergs where they were crossing the Atlantic. And from those records, they actually could show, like, the further south an iceberg got, right, the colder the water is, the closer we were to an ice age. So, but yeah, so like the North Atlantic was an example of that. People are now switching to the Pacific Ocean and trying to see how the two basins either performed similarly or differently during the ice ages overall. And I'm trying to figure out. Okay. So now I have my sieve. Oh, why is it doing that? Are you all seeing the sieve vertically? I guess it doesn't matter too much. I'm just going to be putting some mud into it and water. But here I have just a sample of mud in a beaker. There's a few different types of mud in here, so we can see a few different things, hopefully. So I'm just going to dump that into the sieve. And then I'm just going to wet it. This is just water going in. And I have a brush here that'll help me move stuff around. And you can see already that there's a lot of grains that have come out of that. Some light, some dark. The lighter ones are your, oops, what happened to my phone? Okay. The lighter ones are the plankton shells or forams. The darker mineral grains are minerals. So it's some terrigenous mud mixed in here. But this is literally the first step in analyzing any of the mud from our sediment cores. And so now it just looks like, right, this pile of grains. I'm going to grab some paper towels. I'm going to bring you all over to the microscope in a second. Just bear with me. Hopefully no one gets motion sickness when I start to move my camera phone. But now we're going to shift over to the other side of the room there. I don't know why it's coming up straight for you all. Hopefully, you'll see this properly. Not working very well. So as long as you are fine, then. So I'm going to go take you over to this microscope where we already have it set up. You can see that these tiny little grains come on the side there. That's what I just saw in the sieve that I washed. Very bright. And there are, like I said, 50,000 of these types of species all around the world. I'm going to try and stop sharing my screen here. And join you back here. So if there are any questions, I'm happy to answer them.
Maybe while we give people a few minutes to put their questions in the Q&A, I know Rosalba from the NASA Goddard Institute for Space Studies is with us, and she had some resources she wanted to share with the group. Rosalba, maybe you can go ahead and share those while we wait for some more questions to come in.
Yeah, sure. Thank you so much. Can you hear me? Great. Okay, so I am going to share some links to some resources from the chat. And then I am going to share my screen. Can you see my screen now? Are you able to see my slide?
I can see it.
Okay, great. Okay. So, hello everyone. My name is Rosalba Gerratano, and I help support NASA's Office of STEM Engagement at the Goddard Institute for Space Studies here in New York City. So yes, I am super happy to share about some additional resources that can help explore today's topic. So today I want to highlight Climate Kit, the Scientific Visualization Studio, and NASA Earth Observatory, specifically the paleoclimatology page. So first, Climate Kit. So this is a pretty fun website. It has articles, games, activities, and videos to learn a lot about climate and greenhouse gases, oceans, rivers, lakes, fossil fuels, and so on. And there is one specific section of this website where you can find information about how scientists use tree cores, ice cores, and lake and ocean sediments to understand what the past climate of our planet was. But like I said, there are also many other articles and games, so you may find that a lot of fun. Also, the next resource is the Scientific Visualization Studio. So this studio wants you to learn about NASA programs through visualization. So it works closely with scientists in the creation of animations and images so we can better understand Earth and space science research activities. And so on the link that I shared with you, that's part of an animation of how scientists study the flow of the Greenland ice sheet. And so it will show you how these scientists have used ice cores to understand the past climate. And last but not least, we have the NASA Earth Observatory, the paleoclimatology page. And so on this page, you can read and learn about, again, like how sea sediments and coral and tree rings and cave rocks can teach us a lot about our planet's climate history. It's a very, very comprehensive website, so I highly recommend for you to check it out. And that's it for me. Thank you.
Thank you for sharing all of that. That's really awesome. So a couple of questions came in. It looks like you might have answered one in the chat,
Right.
but just for the recording, how many years have you been a scientist?
Well, I've worked in the core repository here for 22 years now, I think, just over 22 years. I would say, though, that we don't do any research in the repository per se. We're just like a library. So people from all over the world request samples from us, and I send them a little scoop of mud from cores that they choose. And we send out about 4,000 of those samples every year. So I don't do any research myself, but I assist in many other projects. So how often do Lamont scientists discover something brand new in old cores collected many decades ago? Brand new is is a tricky term. We make new discoveries all the time, but it's nothing brand new. It's more that the equipment, the technology that we use to analyze this stuff, and our methods, and even some ideas, right? They change and evolve. So mostly as our capacity for physically analyzing things has evolved, we've discovered better ways of looking at what we've already kind of known, like the ice ages, for example. That has been fine-tuned. So now we need very few microfossils, relatively very few microfossils, to get the same amount of data. And the data is a lot more accurate now as well. What is the max depth core tube could reach? And are all my samples analyzed? So our deepest core, as far as water depth, is just over 5 miles of water depth. It was taken on the edge of the Tonga Trench, which is to the east of New Zealand. It's hard to tell because it usually gets cut off on most maps and stuck on the far west side, but just to the east of New Zealand and Australia there. But yeah, so 5 miles of water depth is our deepest core. Our longest core, because sometimes those can get confusing, but our longest core is 33 meters long from the southern Indian Ocean. So 33 meters of mud, but yeah, 5 miles and 5 miles of water depth. And no, all of our samples are not analyzed. I would say maybe 10% of our samples are fully analyzed to give any real data.
I have one more question, which was related to the last question, I think, which is just, obviously the ocean is huge and deep and you can't get everything. Are there any sort of like glaring omissions in the collection where, for whatever reason you can't get samples yet based on, the technology available?
Right. So the Arctic Ocean is relatively unsampled, because until very recently it was completely ice covered, and you can sail through and collect samples, but you need an icebreaker, you need very specialized ships and equipment. So for one reason or another, yeah, the Arctic is still relatively unexplored, and there are many parts in the southern oceans, so around Antarctica. We don't have a collection. There's actually a specific repository for Southern Ocean cores, but it's notoriously difficult to sample in the Southern Ocean because it's very stormy all the time, and it gets very cold. So in southern summers they'll go, and yeah, the ocean drilling program is filling in some gaps that none of the repositories have collections from, like areas where we have collections. But that's it. I mean, due to political and safety reasons, we can't collect cores in the China Sea right now. So there's a gap there of newer material there. And the Western Indian Ocean is off limits to government sponsored ships due to piracy, ironically. So it's difficult to get newer material there as well.
Well, this is really interesting. I know you know this because every time we do meetings together, but the Core Repository is one of my absolute favorite places at Lamont and Columbia in general. So I'm really excited that I got to sit in on your presentation today.
Oh, I'm glad.
And yeah, I mean, do you have anything else you want to share with the group before we?
Hopefully this pandemic passes and we'll get to see everyone in person soon.
Yes, highly recommend if we're able to do the Lamont open house in person next October. they always open up the core repository and you get to visit in person. And it's just, it's really a phenomenal experience. So, well, thank you to everybody for joining us today. Like I said, the recording should be posted on the website later this week, and we'll send it around to everybody who registered. Thank you, Nichole, and thank you, Rosalba, for joining us today. And hopefully we'll see you at the next session in a couple of weeks.
Cheers.
Thank you.